Hello everyone. Now we are back on Vitis and we are going to create the optimized version of our IP because the latency is high. So what we can do is we will create a new HRS component. So similarly, we'll just click on create component, create empty HRS component. I'll call it matrix optimized. Now I've already created the source files this time. So I'll just add them here. I'll say the top function later in the config file. So now let us select our part corresponding to the board we're using. Yeah, so yes, this is the part and these settings are fine. Click on finish. We've created the HLS component now. And as you can see in the flow section in my component, I'm getting two options. So we can select whatever component we're working on currently. Now let us look at the code to understand what changes have been made. So I'll open the code. So let's start with the header file. It is essentially the same. The only thing we have done is we've changed the name of a top function to optimized. That's it. Rest this is all the same. In the test bench, yeah. So yeah. Now in the test bench, we can see that the test bench is also the same. There aren't any changes in the test bench also. So that's fine. The main changes are the CPP file. So actually in Vitest, we don't really need to do any optimizations from our own side because Vitest has all the optimizations for us. But still, for the sake of this tutorial, we're going to write the pragmas explicitly so that we understand what is going on. So the first optimization we have done is array partitioning. After, of course, the obvious AXI interfaces and the AP control done. So what array partitioning does is we break our bigger arrays into smaller arrays so that we can process multiple smaller chunks at the same time to save latency. The issue with this is FPGA uses BRAMs, and the thing with BRAMs is it mostly has only one or two input-output ports. So we'll require many more number of VRAMs to process the same amount of data. So the resources will increase, but also the latency will also increase. There's a trade-off here because more resources means more cost, and but more latency means more efficiency. So we have partitioned both our input and output array, both our two input matrices, and then one more thing we've done is we have used the loop flattened pragma. So what this does is it creates, so from a nested loop, it will create a flattened loop. So instead of having two nested loops, we'll have only one loop, which will be flattened. So that will save latency. And similarly for the other nested for loop, I'm doing the same thing. And another thing is the pipeline pragma. So to do multiple operations at the same time. One thing about HLS is if I apply the pipeline pragma before the for loop, it automatically unrolls the loop below it. So instead of going through all the iterations, it computes everything in one go. So that is the advantage of doing pipeline before the third loop starts. And similarly, we also added the pipeline in the output loops. So that is it. That is all the optimizations we have done. So in addition to these optimizations, HLS will do some optimizations on its own. So now we can go ahead and run the C simulation. Let us wait for the C simulation to complete. And as you can see, we're getting a similar RMS error just like the unoptimized version. That is good. Now we'll go ahead and run synthesis. Before running synthesis, we have to set a top function. So we'll go to the config file and we'll set a top function. This time we'll not disable any pragmas because we want the code to optimize. So we'll copy our top function. You can also click on browse, it'll give you the function on its own, but you can also explicitly write it down. So uh, as you, As you can see, we are getting a warning next to our C simulation because we have changed some of the settings of the code. So if you want, you can run it again. It won't really make a difference. So we'll run C simulation and we'll run C synthesis. This will take a couple of minutes and then let us analyze the reports. So both C sim and synthesis have now passed. So we can analyze our synthesis report. So for context, what we can do is we can also open an unoptimized report. So HLS actually gives us an option to compare two reports. So as you can see next to the HLS component, we'll get this icon. Click on this and we'll click on the two components I want to compare. Click on compare and I can compare both the components like this. So you can look at the total latency. In the unoptimized version, it took around 2400 clock cycles. Here it is just 310 clock cycles. So that's a significant improvement in latency. But for resources, as you can see, it has gone up in the optimized version as expected. Latency comes at a cost. That cost is paid in terms of resources. So as you can see, the number of TSPs have significantly increased from 5 to 40, and we also see an increase in other components. So this is the trade-off which we were talking about earlier. You can also open the optimized version separately. So as you can see, this is the unoptimized version. Let's open the optimized version. Yeah. So as you can see, if you remember the unoptimized report, this is the unoptimized report. All the loops were nested, and you could see them like this. But here, as you can see, we do not see any nested loops because we have basically flattened all our nested loops. They're all flattened. And as you can see, loop 3 is not written here. We can only see loop 1, loop 2. Now, the reason for that is we put the pragma pipeline just before the third loop. It automatically unrolled the loop 3. So that is why loop 3 is not showing up in this table. And we can only see loop 1 and loop 2. And the AXI interfaces are similar. We're using Flow, so 32-bit for T data, and similarly for others. Now we can go to Pragmas to actually analyze what all we have added here. And you can also click on that particular on this button to see where you've added a Pragma. This is a very useful tool to analyze our HLS file. So once you have done that, we can again run RTL core simulation and package, go back to Vivado and generate a bit stream. Again, create a driver. Driver will look exactly the same and basically test our code. Another thing which we can do is we can test the same component for bigger matrix sizes. So if we look at the compare reports, the difference is not a lot. It is not a huge difference, but as we increase the matrix size, the difference will also increase. So to change the matrix size, this is where the variable, the mat size variable will come to play. We can change this variable. This will change all the instances where we have used this variable. And just by changing this, we can change the matrix sizes. One thing which I would advise is you should also change the name of the top function so that it is easier to look for in Vivado and you don't get confused between whether it is the old IP or the new IP. So what we have done is we have already ran the code. We already ran the code for different matrix sizes and we have compared the results in the form of a PPT. So I'll be showing you the PPT right now and we can analyze it there. So hello everyone. Now let us start by analyzing the different results obtained. So for the 8 cross 8, this were the results we obtained. The RMS error was 10 power minus 6 and the latency reports from a whitelist look something like this. We can see all the loops were nested and there was no pipelining. But in the optimized version, we did pipelining and the cost we had to pay was resources. The number of resources increased. The acceleration on the board, so this was the PS time with for loops. It took around 3.7 milliseconds. And for the PL time, it took around 3.33 milliseconds. So around a 1.11 acceleration factor. Uh, Now for the optimized version in the same case, it took around 1.6 milliseconds. So overall, the acceleration factor increased to 2.33. But still, we could not beat NumPy, which is at a very low 445 microseconds. Now, these results may vary every time we run it on the board. So this is an average result over multiple runs. Now the RMS error on the board is similar, around 10 power minus 6 for both cases. We also tested it for 32 cross 32, and these were the results. For the RMS error on Vitis, it was around 6 in 10 power minus 6 for both. And the latency report on Vitis looked something like this. We had, of course, the number increased from 8 cross 8 for resources, but not as much as the optimized resources, which are very high, especially for flip-flops, jumped from 0 to 18%. And also the latency reduced significantly. As you can see, the unoptimized version took around 10 power 6 uh, nanoseconds, and the clock cycles were around 110,000, and this reduced to just 7,800, 7,700. This is a very good improvement. Then we can look at the acceleration factor on the board. We can see that the PL time and the PS time. So the acceleration factor was around 70 for the unoptimized version and around 124 for the optimized version, and we still could not beat NumPy. The RMS error on the board was also similar. Now for 100 cross 100, we also basically generated the HLS IP. So the RMS error on Vitis was around 3.2 10 power minus 5. And in the Vitis synthesis report, as expected, the latency was very high for the unoptimized version in the number of clock cycles, which jumped down to just to 40,000 clock cycles, just 40,000 clock cycles, which is a very big improvement. And the difference which we were talking about is now much more apparent, where we can see that optimizations actually help latency a lot. But of course, we have to suffer in resources, where the resources jump to around 10, 11, and 5 and 10%, which is a very big number. And the acceleration on the board was something like this. With for loops, the PS took around 6 seconds, while the PL just took around 3.3 milliseconds for the unoptimized version and 1.8 milliseconds for the optimized version. And NumPy time was 2.8 milliseconds. As you can see, the optimized PL actually beat NumPy in this case. So that is great. And the RMS error on the board is also similar, 3.2 10 power minus 5, just like the Vitis RMS error that was expected. Now what we can do is, one issue with this is the resources are pretty high. So we can do something known as word length optimization, which is what we'll do now, so that we can actually reduce the number of resources. Let's do that. We are back on Vitis. So the only issue which we are facing right now is that the resources are high. So we can do something known as word length optimization to help us save on those resources. Let's create a new HLS component. I'll close all the old files. Let's create a new HLS component. I'll call it matrix word length optimization. I've already made the files for this, so I'll just add it here. Top function can be set later, and similarly we can look for uh, our part name corresponding to the board we're using. So let us look at the changes we have made for this IP. So what we have done is, we instead of using a float type, we're going to use a fixed data type instead of using the classic 32-bit float. So we are going to import the AP fixed library, and inside that we'll create a new data type called mad dtype OP, and we're going to set it to be AP fixed 29,9. So what the syntax means is, we'll create a new data type where the total number of bits to be used will be 29, and the number of integer bits including the signed bit will be 9. So the number of fractional bits will be 29 minus 9, that is 20. And so we are going to use it everywhere in my C++ code. So we're going to use this particular AP fix instead of float everywhere. Uh, Only while giving back the output, we're going to use float, so that once we have gotten answers, you want it to give it back to the DMA with the maximum possible precision. So we're going to use float. Rest everywhere for all calculations and for all variables, we're going to use our AP fixed data type. Now test bench is basically the same. There aren't any changes here. And what we can do is uh, we can actually play around with these numbers to get the best possible word length optimization. So how we do that is we basically start from 32 comma say 11 or 10, and we keep reducing the integer bits. So we'll run C simulation at every step, and the last bit where the last word length where the C simulation is passing, we'll note that particular word length down. It will be 32 comma x. Now I'll fix my x and I'll start decreasing my total bits. So from 32 I'll start decreasing to 28 to 30, 29, 28, and so on till my C simulation fails. And the last place where my C simulation is passed is my optimized word length. So if you set the threshold for errors to be more, you can use lesser number of bits and your C simulation will still pass. So this is the trade-off here. So we need, if we want a better RMS error, that is a lower RMS error, we'll have to use more bits. So now we can analyze the results in the PPT. So now we've implemented word length optimization. So we used float earlier, and now we're using fixed 29,9. So as you can see, the resources have reduced from 10, 11, 5, 10 to 10, 9, 0, 4. The flip-flops are significantly reduced. If we can further reduce these resources if we use a smaller word length, but the only trade-off there is we'll get a bigger RMS error. So if we can afford that, it is fine. We can use a smaller word length. So we can look at the acceleration factor. It is approximately the same as float. It is around 4079. And if you remember for float, it was around 3 to 6 times. So similar, it is actually improved. That's nice. The RMS error is around 2 10 power minus 4. So this is not a bad error. We have set the threshold to be 2 10 power minus 4. So it is just slightly lesser than that. That's fine. This shows that we have chosen the most optimal word length. But as compared to float, which was 10 power minus 6, if we use 2311, the RMS error will jump up to 0.05. But actually the resources will significantly reduce. So we'll have to find the perfect word length where the resources are also uh, enough and less as per our liking, and the RMS error is also fine. So 29,9 is a decent value for that. So to summarize, these are all the results we obtained. As you can see, the acceleration factor for optimized is always more than the unoptimized version. And as we're increasing the matrix sizes, our acceleration factor is also significantly increasing. This is something we had expected. And the RMS error follow a similar pattern. The optimized and unoptimized approximately have the same RMS error, but the only difference here being the word length optimization, where the RMS error has increased because we've used lesser number of bits. This is something we had expected. So thank you so much, and I hope this tutorial was very clear to you. Thank you.